Hi, my name is John Armour, and today I'm going to be presenting us alongside Nicole Finley, Errol Bartran, Robert Long, and Jesse Rocky. And we are the IDEX Mass Timber Group. We're an undergraduate research group from Washington State. And over the course of this last year, we have developed been working on researching developing a pilot supply chain for cross-laminated timber in the Northwest. This is our final presentation of the academic year, and so to start things off, we want to go and do kind of a recap of some of the main points we've covered along the year. And so what we're going to do is we're going to start off and we're going to look at why CLT. Why is CLT important? We're going to take a look at the supply and demand side of things. And then we're going to transfer over and we're going to look at some of the more logistics aspects, how we might get our supply to our demand, as well as some of the different building types that we were looking into this semester. And then if you've been following along with our presentation so far, we've started to look at some different building models. And we're going to take a look at some of those different plans of those building models in order to see kind of how we've used CLT in different ways, depending on the building type. Then we're going to take a look at some of the details for our building, and then we're going to wrap everything up with a conclusion at the end. So before we get started, for anybody who's just joining us, and this is their first presentation with us, to clarify what CLT is exactly, it is cross-laminated timber. And by definition, it is an engineered wood panel, and it's assembled, this is an image of CLT here, it is assembled just like the game Jenga, as with the blocks being dimensional lumber. It usually is a 2x6s and 2x8s. And then each layer of that dimensional lumber is put orthogonally to the layers above and below it. And this allows for CLT to use the strong axis of the dimensional lumber in both directions of the panel, which makes the CLT panels extremely versatile and can be used in can be used as wall systems as well as roof systems and floor systems. And really an entire building can be built just from CLT. Another aspect of CLT that makes it a building material that we're excited about is the fact that it is a sustainable building material. As I mentioned, it's entirely from wood. CLT panels are entirely from wood other than the resin that's used to hold them together. And so wood is really the only fully sustainable building material that we are using right now in construction. Some other aspects of CLT that make it a really exciting building material are the fact that it is a safer construction material. And this is because all CLT panels are fully manufactured off-site and then brought onto the site. And so really the only thing that's going on site is just the panels are being craned into location and then bolted down or screwed into the position. So really the only two construction tools that are needed are a crane and a pneumatic drill. This also allows for cheaper on-site construction, and in general, this causes quicker building times, which makes, in turn, CLT being really cost competitive with other building materials. So if we start to look at more of the supply side of things, CLT, this right here is a map of the forests in Washington. Everything in green is the forest coverage area, and the darker green area shows the more dense areas. The more dense forests are important to CLT because in more dense forests, they typically have smaller diameter trees, and CLT can utilize these smaller diameter trees when other wood products sometimes struggle in utilizing these small diameter trees. All the red is shown is the area that is predicted to be harvested, as well as the area that's currently available to be harvested. All the blue here that's shown is area that's been affected by beetle pine kill, and this is area that needs to be harvested within the next 2 years so it doesn't become waste. And beetle pine kill areas can actually be harvested and used as structural lumber if it's harvested within the first 2 years. And then finally, everything in orange in this image is areas that have already been declared as areas that need forest restoration. And really the big takeaway from this map is just the fact that there's a great amount of lumber and forest that we could utilize as supply. And so supply really isn't a huge issue for us in this supply chain. So if we kind of transform and we look at more of the demand side of things, here's a map of the populations centers in the Northwest region. And we know that population population centers tend to have larger infrastructure. If there's a large population in an area, they tend to have more need for infrastructure. So you can kind of see here that the Seattle and Portland areas have really large population sites. And so if we start to look at what kind of infrastructure and how often that's occurring in those areas, we take a look at this figure here that shows the offices and the multifamily construction that's occurred from 1980 to 2015. And again, this area shows the Seattle area as being really vibrant in new construction with offices and multifamily construction, which is why we've determined our site to be in the Seattle area. And then finally, that was a history of kind of the construction in that area. But if we wanted to build in the future, we'd want to know some predictions of how much construction might be going on in the future, if all the infrastructure has already been built, or if we're going to continue to build more and more. And this figure is a prediction of what's going to occur in the Northwest for mid-rise or for multifamily structures and office buildings. And it clearly states that as the years progress, more and more infrastructure is going to be built with those two building types, which is why that's what the type of building that we're going to take a look at. So now I'm going to hand it over to Errol, and he's going to take a little bit look at the kind of logistics of the whole CLT process. So.
Thank you, John. I want to give a synopsis of some of the work and research that we did earlier in the semester. So one of the things we looked at was shipping options to get the wood from the forest to the mills, and then also transport the finished CLT products to the job site. We looked initially at 4 different types of transportation. One was rail. The best way to transport CLT panels is using a center beam rail car. It has a very large capacity, both by weight and volume. And then there are some other truck options. We further narrowed it down to just the 2, the flatbed semi-truck and the center beam rail car, based on which were the most cost effective to haul massive amounts of CLT from the manufacturing plant to the job site. Notice, however, that the flatbed semi-truck might be needed for more urban areas like we will be looking at. So where are these trucks going? First, they need to pull the wood out of the forest where it's harvested and then bring it to the mill where it can be turned into dimension lumber. After that, it needs to be brought to various manufacturing plants to process it, press it, and then finally do some subtractive manufacturing to custom make it for the job that it's intended to be used at. And then after that, we finally need to transport it to the job site. We looked at 4 main supply chains as far as CLT manufacturing plants, and then getting that from that location to Seattle near the South Lake Union area. The 4 places that we looked at for the manufacturing plants are Forks, Darrington, Twisp, and Colville, based on already existing infrastructure for processing wood. One interesting thing to note, Colville is much further away. However, it has infrastructure for trains already there, so that helps with the cost. So each of these have different strengths and weaknesses, as we addressed in previous presentations. Now a little closer look at where we want to put our buildings. This is the South Lake Union area, and as you'll notice, there are different zones. Let's look a little bit closer at that. We are putting our buildings in the brown zone that you can see there on the screen. This is the SM 85/160-240 area. This spot we chose because we wanted to make our building heights as tall as we could for this zone so that we could make them more competitive. The one exception to this is the 85-foot multifamily building. It has more flexibility in which zone it can go in. However, for uniformity and allowing us to make comparisons across all the different buildings, we wanted to keep it similar. So we're looking at that brown zone that you can see there on the map. And then this is a little better image, shows you what's actually there on the site. We are on Fairview and Thomas Lane. If you're familiar with that area, it's a vacant lot, like I said, just south of Lake Union. So then our different building heights. In the past, we looked at several different options, including warehouses and high-rise office. Due to reasons that will be gone into later in this presentation, we're mostly focusing on mid-rise buildings from 85 feet to 160 feet with 125 feet in the center. And you can kind of see the relative heights of those in the figure to the right. Then we want to look at what types of construction we use in our buildings. So you can see in the figure there we have type 1B buildings and type 3B buildings. Type 1B is characterized as fire resistive and non-combustible. The advantage to this type of construction is that you are allowed to go higher, however there are more restrictions when it comes to fire ratings. On the right we have type 3B. The envelope is required to be non-combustible and have a fire rating. However, the inside is much less restricted, so that makes it a cheaper form of construction. However, you are not allowed to go quite as high. Here we have type 4 and type 5A. Type 4, shown here, that is the Bullitt Center that went up in Western Washington. This type of construction is characterized by oversized timbers. So the idea behind it is that you make the structural members bigger, and that allows charring to occur, still leaving a core that will allow the building to stand after a fire. And then on the right we have the type 5A. This is your more typical light frame wood construction. However, we believe that with some variances from the code that CLT could be very competitive. So here's a summary of all the different types off to the right with all the different restrictions that you can see. You've got the type 1B, your fire resistive, non-combustible. Your type 3B, which is unprotected combustible on the inside, however you need a fire resistive envelope. Your heavy timber type 4 and your type 5 protected wood frame. And it's interesting to note how the different fire ratings vary throughout the building, whether it be the ceiling, the floor levels, and then what heights you are currently allowed under the code. So now that we know what the code currently allows, we wanted to ask for some variances because CLT is a new material, and we believe that due to this and some of the characteristics of CLT that we can perhaps ask for some variances from the code. Here you see the type 1B buildings that we built. On the left you see the type 1B multifamily. That is a 160-foot building. Also on the right is a CLT office, and that is also 160 feet, both type 1B buildings. The detailing, as you will notice, is a little bit more protected on these. And the variance that we're asking for is that CLT is currently not allowed in type 1B construction. However, we believe that due to the difficulty in getting CLT to ignite, that it has a very good chance of being accepted. Then we want to look at type 3B buildings. This one we actually did not ask for a variance. We wanted to have one building that could be constructed as is with the drawing sets that we made. And so this one could be constructed tomorrow if needed. Then here we have our type 4, the heavy timber framing. This one had several beams in it. They were all oversized to account for charring that would occur. And the variance that we're asking for here is a height variance. So previously it was restricted to 85 feet. We're asking for 125 feet. And while this is a fairly large increase, we believe that due to historical buildings that were constructed out of heavy timber in the Northwest, as well as new codes that are being proposed in Canada, that this has a fairly good chance of being feasible. Then we also want to look at the type 5 building. Originally it was restricted to a smaller height. However, we're asking for a much more modest height increase, and the reason for this is that the CLT is far superior in strength to light frame construction. And so when you use CLT in a really small building, you don't maximize or fully utilize the strength of that CLT material. So we're asking to go a little bit higher so that our designs can be a little bit more efficient and more cost effective. And now I'd like to hand it off to Nicole, and she will talk about the floor plans for these buildings that I just showed you.
Thank you, Errol. So to begin, Errol has talked a lot about how zoning, occupancy, and building type plays a role in developing the structural patterns that we see in these buildings. We've also looked at other considerations like lateral loading. And seen here are our 5 buildings with their corresponding vertically distributed base shears. And a lot of this is determined by the plane size of the building as far as its floor dimensions, also the allocation of mass in these buildings. So that's why you see a variance between large circles and small circles at different heights. And this brings us to the structural patterns that we have determined for these 5 sets of buildings. And so as you can see, these are just simple layouts of the structural patterns that we will be using. These have been taken into consideration for lateral load path, gravity load path, as well as the zoning occupancy, and we've also revised them to consider logistics of architectural purposes, such as parking garages. So as you can see here, the offices support much more open spaces. They use glulam beams and columns primarily to support their gravity system and include some shear walls to support their lateral system. The offices have fewer shear walls, and thus they usually require either thicker CLT ply sizes or the use of concrete shear walls further up in their building. The multifamily buildings primarily use a bearing wall system for their gravity as well as a shear wall system for their lateral resisting force. And because of the abundance of walls in these structures, they are able to use smaller CLT ply sizes or less concrete up the building as we develop these shear walls. And so taking a look at the 160-foot office, we can see the parking garage developed for this office. And as you can see, there's concrete shear walls around the elevators as well as a few concrete shear walls scattered throughout the parking garage. If we overlay the floor plan on top of that parking garage, we can see how these elevator shafts and shear walls align and are continued up through the tower. The concrete shear walls continue until level 7. At this point, 7-ply CLT is used throughout the duration of the tower. Notice that the parking garage has a larger plan dimension than the floor plan itself. As we look at the 85-foot office, we again see those elevator shafts and scattered concrete shear walls. In this case, when we overlay the floor plan, again the dimensions of the parking garage are larger than those of the floor plan, and in this case those concrete shear walls continue up until level 3, and then levels 4 and 5 use 7-ply CLT, and level 6 uses 5-ply CLT. Then we have the 160-foot multifamily building. In this case, we see those elevator shafts and concrete shear walls. However, in this case, the plan drawing of the floor plan lays directly over top of the parking garage. In this case, also, those stairways that we're seeing in the parking garage only continue up to the retail level. After retail, the stairways change for the floor plans in the corresponding tower. This structure uses concrete shear walls in the podium and garage. Floors level 2 and 1 use double 5-ply shear walls, and the rest of the building continues up with double 3-ply shear walls. Next, we have the 125 multifamily building. Again, we see the parking garage. You can see those concrete elevator shafts, the stairways. Now the parking is just generally going to lay out. When we overlay that floor plan again, we can see that the parking garage has larger dimensions than the floor plan, and that those elevator shafts and stairs continue all the way up to the tower. This building is unique in the fact that it doesn't have a podium, so it uses concrete shear walls only in that garage. After that, the first 4 floors are double 5-ply CLT, and the following 6, the rest of the tower, is double 3-ply CLT. Finally, we have that 85-foot multifamily office, and again, we see the parking garage with your shear walls, which in this case are also concrete, your stairs and your elevator shafts, and overlaying that floor plan, we can again see that the parking garage is going to be bigger than the developed floor plan, and those stairs and elevator shafts continue up. In this case, concrete shear walls were used in the garage and the podium, and this building was able to take double shear ply walls all the way up from the first level to the top of the tower. The shear walls are aligned in the garage beneath the shear walls that are CLT in the tower in order to transfer that shear. And now, at this point, I would like to have Rob come forward and continue discussing some of the details of these structural patterns.
All right, thank you, Nikki. Up until this point, we've been looking primarily at the bigger picture of these buildings. We've been looking at the structural components and kind of sizing the members of these different components of the structure. But now I want to take a look more at the details of the connections that are going to piece this building together. A structure is nothing without its details and connections, and so that's what we're going to be looking at here, just narrowing down our view. I want to note that these detail connections, they haven't been engineered or sized proportionally, but what they are is a visual for us to see where we would have to move forward or where further research is going to have to be done for a connection type for a CLT panel. Because CLT is so new, connection types are still really being implemented and researched. And so these are just more of that visual aid to see this is the type of connection we've seen work maybe in glulam or other preliminary CLT structures. And so we wanted to create that visual. Also, furthermore, I want to just point out that there's going to be two types of construction that you see here. And the two different types are balloon type construction and platform type construction. Now the difference is for balloon type construction, the diaphragms are being hung off of some sort of hanger that's connected to either the wall or the column, whereas platform construction, the diaphragm gets placed on top of either the column or the wall, and then the next column or wall is built off of that. And so there's a bearing pressure on the column or wall due to the diaphragm. So getting right into it, here we have the Type 5 multifamily unit. And I want to point out that this is our one platform construction building. As you can see right here, is that our diaphragms are coming into a notch that's been notched out of the CLT walls, and it's bearing in that notch. So if we look closely right in here at this CLT wall right here, it's not a column, it's a bearing wall. What we have is two 3-ply CLT panels. Those two 3-ply CLT panels come and they sandwich together to leave just enough gap, and this gap is in order to be able to run conduit, electrical, mechanical, things of this nature through our building. And so because of the bearing wall system, we needed that gap to be able to run things of this nature through our building. And so these two 3-ply panels are connected through bolts, and then the diaphragms come, they hang off of this wall, and as you can see, to secure and fasten that into the wall, we have two toenail screws going through either direction. Furthermore, I want to note that for the spans of our diaphragms, which you can see right down here, for this building, we have a 16-foot span, and the issue here was not deflection, it really was, or the max deflection. What it was the vibrations that would occur in the CLT. And so what we had to do for all of our building types, some a little bit differently than others, but what we needed to do was add concrete on top of this to get composite action in order to span these lengths appropriately to avoid issues of vibration or deflection and other issues as well. Next up is we have the Type 3B office. And so here you're going to notice something a little bit different, a different framing system. And what we have here is we have CLT columns that are rising up and bearing on top of each other. They're not continuous columns, rather they're stacked on top of each other, and you can see that there's steel plates right in here that are going to connect the two together with bolts attached into the two. From these steel plates, what we have is what's called a kerf plate. The kerf plate is just a square tab that sticks out, and you can see right in here that the glulam beam is going to come and attach right into that kerf plate, and the bolts are going to be then attached to it. So we have a column, we have glulam beams coming perpendicular to that column. Then on top of those glulam beams is we have our CLT panels, which are going to act as the diaphragm. And those span a length up until the next beam, which in this case are 24 feet. And so again, we have the concrete on top, which is going to give us that composite action. And then down here below is what we have for our connection for the CLT columns that are going to be attaching into our concrete foundations. And this is simply just a bracket with bolts connected into both the foundation and as well the column. Next up is we have the Type 4 multifamily. This is kind of a combination of the last two that we've seen. And so what we have here is we have CLT walls that are running up. And this CLT wall, it has two 3-plies, just like the multifamily that we saw earlier. And then kind of piggybacking off of the office that we just saw earlier, we have the glulam beams that come and attach into the CLT wall. So it's a bearing wall rather than a column, and it has the glulam beams coming in, attaching to a kerf plate or a hanger. And then the CLT panels are then going to be placed on top of the glulam beam and spanned outwards to the next glulam beam. Next up is we have the Type 1B multifamily. Pretty much what we've seen so far, not much difference. Probably the biggest difference for this one is that we're using two 5-ply CLT panels that are going to come and be sandwiched together. Most of the building has the Type 5, either the 5-ply CLT panels or the 3-ply CLT panels, so this is kind of just a different variation. And so here what we have is for the diaphragms, you can see right in here that the diaphragms have a metal plate that are going to be attached to the end of it, and those are going to then come in and attach to the metal plate that's attached to the CLT wall. And so that's going to be connected via bolts, and then the span for the CLT diaphragm is going to be the same with the composite action. Last up is the Type 1B office. And what we have here is we have our concrete columns that are rising probably about half the way up the building. And so from these columns, what we have is we have glulam beams that are running perpendicular into the page, which you can see right here. These are the glulam beams running in, and then from on top of that, we have our diaphragms resting upon that. And to get a better visual of what's going on here is you can see kind of the assembly process that will happen for this type of construction. It's a little bit complicated, so we wanted to show exactly how this would be implemented. And what you can see is that you can see the girders running one way, which are the glulam beams, and then on top of that you have then the CLT panels followed by the concrete, and then finally the last bit of it will be the mullions that are attached to that. And so this is it of what we have for the detailed connections. And last up, I'm going to invite Jesse to come and give us a conclusion of our report.
Hello again, everybody. My name is Jesse, and I'm going to conclude the presentation with an estimate of massing and revenue for each of our building types. And then we're going to compare those building types and their revenues, and then we're going to look at where the IDEX Mass Timber program is going next. So first, we are going to start with the residential models, and based on our sources, we've estimated the revenue per unit to be $190,000, and then the cost of the retail to be $200 per square feet. And it's important to note that most of these models have one or two floors of retail on the bottom floor. And so that's where that will be taken into account. It's also important to note that not all the units are the same size, and that the prices obviously will vary based on the location, the purpose, and the quality of living. But for our purposes, for comparative purposes, we will be using the same price for each unit. For the office units, we will be using a $190 per square foot office space cost, and our retail of $200 per square foot, which is the same as for our residential. It has been told to us that that the office cost is actually more than the retail, but because the retail is such a small portion of our building models, the estimate is still fairly accurate. So if we look at the 85-foot multifamily model, we can see that it's about 76,000 cubic feet of wood required, which is about 53 truckloads, and this is based off of the sizes that Errol gave us earlier with the transportation, the large flatbed truck. It's a 5-axle, and it's actually controlled by the weight limit, which is 48,000 pounds, and that's pretty standard for our region. The revenue on this building is about $16 million. Then if we move on to the 125-foot multifamily, you can see all the different plies of panels that we would be using there, the square footage for each. And then we also have the total cubic feet here, which is about 170,000 cubic feet of wood. That includes the glulams, which there is a lot of for this structure. And that's about 116 truckloads. And then the total revenue for this building is estimated to be about $34,000, and that includes that retail on the first floor. For the 160-foot multifamily, we have even more types of panel plies, and these increase, the plies increase as the building, as more weight is applied to the lower parts of the building. And so that is going to be about 107 cubic feet, 73 truckloads, and it's going to produce about 19 million in revenue. And it's also important to note that you may have noticed that the wood demand for this building is smaller than the other two residential buildings, even though it is a taller building. But this structure has a significantly smaller floor plan than most of the other buildings, and that's where that kind of breaks from the pattern there. And so for the office buildings, we are starting with the 85-foot, which has the lowest demand of any of the buildings. It's only 40 truckloads, about 57,000 cubic feet, and then it produces about $20.4 million in revenue. And then the large office, the 160-foot office, has the largest dimensions of any building, and that's obvious in the demand here for the wood is about 270,000 cubic feet, which is about 185 truckloads based on our truck size, and then revenue is about $60 million, which is almost twice as much as the next highest. And so if we compare them all visually here, it's important to note that they aren't concrete numbers. We aren't taking into account any of the other materials that are being used other than wood, so it's not really useful to compare to other buildings, but between our models, it's something that we can look at and kind of look for patterns. One thing to notice is that the 85-foot office has a far greater revenue for its wood cost proportionally compared to the other structures that we're considering. And so there's a concept I wanted to bring back from our previous presentation that's pretty important to what we're doing with these revenue ideas and how we're trying to apply our models to the real world. And if you look at any major city, pictured here in Seattle, you'll notice what has been dubbed the mid-rise gap. And this is a limitation based on the types of materials that are being used for buildings and kind of the limitations that we have with those materials. For example, light frame construction, which is the typical use for wood right now, is limited to about 4 stories or about 65 feet, which is a typical zoning height. And this is just due to the codes and how tall you can build wood with it still being safe. And then when you get to the larger buildings and the greater heights, you have to switch to steel and concrete, but typically buildings that are less than 10 stories aren't built out of steel and concrete because it doesn't really become valuable until you're using the most of that space and building very high. So 10 stories or about 125 feet and up is usually typical for those steel and concrete. So if you take a closer look at this, you'll notice that there's a bit of a gap between that 65 foot and 125 foot, and there are exceptions, but in general, this space is being underutilized, especially in the South Lake Union area, which is our focus. And so there's many zoning areas that are about 85 feet, and they get up to about 160 or 240, that we can take advantage of a CLT. And while it's not necessarily a cheaper material, it definitely goes up a lot faster. It cuts costs on labor, on transportation, on time, and we're hoping that those advantages, in addition to some of the incentives that are being offered for using CLT as a sustainable material, will kind of spark people's interest and make them want to try CLT in these kind of areas. And so as we graduate and we make room for the new generation of Mass Timber IDEX students, I kind of wanted to give them a transition into what we're doing, and it doesn't really work so easy as we're just kind of passing a baton to them. We don't have all this information that they're just building on. We have compiled all this information. We've branched out into different disciplines and fields that we weren't really expecting, and so we did a lot of satellite mapping and for harvest, and we studied mills, and we looked into logistics and transportation and all kinds of cool things. But that isn't really useful to the new batch of students. So what we're doing is compiling all this information and making a concise report for them that kind of reference, and I like to think of that as more of like a seed that we're planting for them to grow and start their own new fresh projects. And so what they are going to be doing next year that you will have the pleasure of watching is they're going to start focusing on the assembly level of these buildings, so the connections and some of the complex loadings that are going into all the various components in these buildings. They're going to do a more focused cost analysis with actual numbers as opposed to what we did today. They do have new models, including the K through 12 university and single-family low-rise buildings, and then they might actually even be making prototypes for next year's solar decathlon. And so as we move on, we wish this new group the best, whoever they may be, and we hope that our research leads them in the right direction and allows them to do great things. And at this point, we'd like to thank you all for your continuing interest in our program. We hope that passes on into the next group, and we'd like to thank the great staff and faculty here at Washington State University. They've been a huge help. We've gotten a ton of knowledge and we've learned so much. If you have taken even a fraction of what we've learned from these videos, then we have accomplished what we wanted to. So we thank you for watching. Have a great summer, everybody.